So, to continue, we talked about handling asynchronicity just now, and it's kind of a tricky thing to deal with, sort of to understand, especially these sort of asynchronous waits, and usually the best thing to do is to do it by example. And the example that I was going to talk about was porting a parallel code, but I'm kind of conscious that time is going on, and it would be good if you had some time to try the last practical before the end of today. I'm around tomorrow morning, so I can talk a bit more about asynchronicity then, or we might be able to fit it in at the end of today, but it would be a shame if you hadn't had a go at trying a bigger code practical. Now, the last practical, which I think is practical 3 in that tar file, is the Nass parallel benchmark multi-grid code. It's a bigger code than the Himeno code. I mean, it's a big 600 lines, which still isn't big in the sense of, a real application. But the structure of the code is much more realistic. It's got a more complicated call tree. Its data moves up and down the call tree. When you first open the file and look at the code, you can't sort of see the structure immediately. So the practical, along with the practical, in that directory, there's a PDF file, and that PDF is an enormous document. It's about 19 pages, which is quite frightening. But the idea of this is that it's not simply a list of things to type. It's really a set of, it leads you through the entire process of porting that code from the point of view that we will treat this like a real code. So how do we know where to start? How do we work out how to scope the variables? How do we do all these things? What tools are there to help? So to do the whole thing and work through all of that, this is quite a job, and it takes a lot of time, and it's more time than you can really give in a day's course. So this is why the document kind of is fairly wordy. It has results in it. It has screenshots. It's designed to be something that you can sit down and read afterwards. You can sit down and read it on its own. It's better if you can look at the source code as you go. It's better if you can even run the source code whilst reading the document and check the results and see what happens and check all these things. So you get some time to do this today. There's some time tomorrow in the morning when you could do that. You can do a bit more while I'm talking or whatever, however you want to structure it. But it's kind of a take-home document as well as being a guide to this practical. And yes, it could be made shorter, but I don't think it would convey the same sort of information. Because porting a big code is a big job, and a real code is even bigger than that. But this is supposed to give you some more things that you can do when you're dealing with that code. So you may have seen the Nass parallel benchmarks. You can download them from the NASA website. There's a set of codes in there. Although they're called the Nass parallel benchmarks, I'm actually looking at the serial version of the code. There's a serial version in there. So it's running on one node. I'm going to be parallelizing it to run on one GPU. So it's not an MPI version of the code. We do have an MPI version that's been OpenACC'd as well. I think that's in the parallel code directory of the tar file, just as an example that can be used perhaps in the next days. So, sorry, I said it was 600 lines. It's about, 1,000 odd lines of code. So it's a bit bigger, it's a bit more complicated. The PDF has all the instructions for building the code and running the code. When you run the code, much like the Himeno, you get some part of the output file. There's a checksum. It also verifies whether the checksum is correct, and it times the execution and converts that into a performance figure. And again, we use that performance figure as a metric. There's a Fortran version, there's a C version. You can choose which version you like. So what do you do? Where did we start? The first thing you should do is you should profile your code running on the CPU, because you want to understand something about how the code works. So the first thing you do is you just profile it using So you do a pat build, you do a tracing experiment using the -u flag to say, trace all my user functions. And when you do that and you get the .xf file and you look at it, you get a profile that looks something like this. The performance figures in this talk are for XC30. So if you run on Turdy, the numbers will look slightly different because the CPU is different. And also the architecture of the blade is different. So even some of the GPU figures can look different because the integration of the GPU into the CPU via the sort of bridge chipsets is different. And XC30 tends to perform a little bit better even for sort of pure GPU. So when you run it, you see that there are essentially 4 routines that dominate the runtime with this proportion of the runtime. There's other routines that are executing, but they take less than 1% of the total time. When you do a pat report, by default, anything taking less than 1% of the time isn't shown. There's a flag -T if you want to see everything. The point of these is that insignificant routines can still be needed in an OpenACC port because you want to process data on the GPU all the time. So you can also do a pat report and ask for a call tree view. So this is the same .xf file, you just report it in a different way. Again, the PDF has the exact instruction to use. When you get the call tree view, it's showing you these 4 routines again, but now it gives you some idea. There's a main program, which is called MG. MG, if you look at the indentation levels, calls 2 different routines. It calls MG3P and it calls resid. MG3P then calls these 4 routines. So you can see that resid is called from 2 different places in the call chain. Understanding the call chain of your application is very useful because when you put the data regions in, you want to know where to put them to enclose calls to the routine. So we're getting this information without even looking at the source code yet by doing a profiling and getting this call tree view. The next thing you want to know is, okay, it's all very well knowing which routines take the time, but are they suitable for GPU? Do they have loop, is the runtime of the routine, is it due to loop nests or is it due to serial code? If it's due to loop nests, how much work is in those loop nests? If they have really small trip counts, it's not going to work very well on a GPU. Again, simple application, you just know what the trip counts are. For a more complicated application, it's not so obvious. This is a multigrid application, which means that it processes an array, but it processes it by sort of coarsening and refinement processes, whereby sometimes it's averaged the array down to be very small, and then it interpolates it back to be big and does processing at all these different resolution levels. So the number of trip counts depends on how it's calling the routine. And if you've got a real application, it's not obvious how many trip counts there are in a loop. So this is very useful information. So the Cray compiler has a way of, you can compile the code with a special flag, and then when you do a CrayPat profile, the profile isn't done at a routine level, it's done at a loop nest level. And that's really useful. So the information we can get, here I'm only showing the information to do with the most expensive routine, which is resid. Here we can see, we've not looked at the source code, remember, but we can see here that we've got some loops in there. The loops take quite a lot of time. If I go back and we say how much time is spent in resid in total, it's about 2 seconds. If I look here, this loop has an inclusive time of about 2 seconds. So basically all of the time in that routine is spent inside a loop nest. And the outer loop is at line 634, and its inclusive time is that. I execute this loop nest 161 times. The trip count is sometimes small at 4 and sometimes big at 256. The mean trip count is 96. So that's really useful information. 256 is not bad. Loops with 256 iterations are probably big enough to work well on a GPU. Small trip counts are not so good. They may be inefficient. The mean, well, 96 is all right. But this is a loop nest. I've got a loop starting at 634. I've got a loop starting at 635. The inclusive time is almost the same. If you multiply this by this, you get this number. And what that's telling you is that these are two perfectly nested loops. And then within these, there's two further loops, same hit, which is this times this. So the number of times that I start this loop is more because it's nested inside other loops. If I add the inclusive times here, it's about the same as that. So what that's telling me is I've got outer loop, perfectly nested inside it, I've got a middle loop, and within the middle loop, I've got two separate inner loops. And I've learned all of that without looking at the source code. Of course, in reality, you would be looking at the source code, but the important thing here is by this loop level profiling in Cray is brilliant for understanding your code and understanding if it's GPU friendly. I know I should say that because I work for Cray, but there is no other tool that will do this for you. Really, there isn't. And this information is information. It doesn't matter whether you run this code on a Cray later or not. This is information that's guiding your porting. So clearly we should start with this resid routine, and we would go into this resid routine, and I've not shown the source code there. Parallel loop. For tuning purposes, we might put a vector length clause for later. We look at the arrays, and it turns out that there are some data arrays, U, V, R, and A. So we work out whether these are copy in, copy out. You would look at the source code to see this. There are some temporary arrays, which they only have an I index, the inner loop. They're populated in the first of the loop nest. I said that I had two inner loops, one after the other. The first one populates this. The second one just reuses that data. It's just a little reuse loop. These are private arrays. I must say they're private. In C, it would look the same. The only thing is, because these are dynamic arrays, I need to specify how much data should be moving. So I need to avoid unshaped pointers by being explicit about the copy in and copy out. When I do that, the code goes slower. Why does it go slower? Data transfers, of course. But let's pretend we didn't know that. If I run it with the Cray-ACC debug, so I go to the submit.wlm file, I uncomment the Cray-ACC debug line, I do bash resubmit.bash to rerun the job, and then I look at the log file, I can see what's happening. For every call to the resid routine, then there is some movement of data, big arrays being moved here, then a kernel executes, and then there's a big movement of data back. A lot of data was moved. If I do the compute profile, I can see that for each thing that's moved, there's a lot of time spent, a lot more than is spent on the kernel. And then if I do the Cray pat profile like we did for Himeno, so pat build minus W, and then I look at this profile, the profile is hammered by data movements. They're taking all of this time. Only 5% of this time was actually on GPU kernels. And if I want, I can, and then if I look in table 2, you can see, you've got sort of 6 gigabytes of data moved collectively over all these 147 calls to the resid routine. So this is a massive amount of data that's had to be moved over the PCI Express bus. And in fact, it's now to the point where the resid kernel doesn't dominate the profile anymore because it's been accelerated, but the resid data transfers do dominate the profile. So what do I need to do? Well, what I need to do is I need to go back to my profile and say, well, resid was one of the kernels. but I need to get the data on the GPU and keep it there. If I'm going to keep it there, I'm going to have to port more kernels. So the first thing you do is you say, well, there was resid, but there was also psinv. This one is only used in the initialization, so we can ignore that. Then there's this one and this one. I need to port those routines to the GPU as well, because they are dominating, they're very important in the runtime. So I go in and I put ACC parallel loop and the copy in and the copy out as I need to. And when I run that version of the code, and again, in the tar file, there's a version, I think version 2 was this, version 3 is this. So you can see what all of the code versions are there for you to look at. The Fortran Performance is even slower. You can guess why. There's more kernels. Each kernel is doing data transfers. But the C performance is even worse, which is unexpected. Why is that? It's going to be a scheduling problem. So I start looking at the profile, and I look at the profile, and I see that, well, it's spending a bit more time in interp than I would have expected, because interp, you know, is suddenly the most expensive kernel, when before I would expect resid to be the most expensive kernel. So I look at the loop mark, the compiler listing, and I say, yep, big G, that's good. Partitioned over threads, partitioned across thread blocks, that's good. Here we've got an inner loop, yes, that's partitioned over threads within a thread block. But then I've got another inner loop, and it hasn't vectorized that loop. So it's doing this loop sequentially, and that's why everything is going slowly. So what do? I go in and I say ACC loop, hash pragma ACC loop independent, or I could say hash pragma ACC loop vector, either one. I go in and I help the compiler. When I do that, I suddenly find that instead of this unrolling loop mark, I then get little g's down there as well, and I've got 2 levels of little g, and the C performance jumps back up. So here, it helps that I've got Fortran and C, because it signaled a problem, but otherwise I should profile and look for kernels in strange places in the profile, and then look at the scheduling. Now we need to reduce data movement, so we want a data region high up the call tree, and only move the data with the data region, and then use the kernels with present clauses. But if we're going to do that, there's a few other loop nests that were really insignificant. They took less than 1% of the runtime, but they should now be running on the GPU. So I can do a pat report minus capital T, and it will tell me about those. I then go into those, and I put in ACC parallel loop for each of these. Even worse performance, because I still don't have that data region, so even more kernels are shifting data. The C performance is slightly down. If I go in, it's another, in the COM routine, there's another place where I need to correct the scheduling. And again, the tar file shows you all of this. Now we go into the main program. The main data arrays, U, V, and R, I'm going to put a data region. It's going to include the initialization so that these arrays only will exist on the GPU. You know, the data will only exist on the GPU. I don't want to do any data movement between CPU and GPU, so I'm going to declare them to be create as temporary arrays. I'm going to initialize them on the GPU, process them on the GPU. There's some tiny arrays. These are size 4. They're initialized on the host. I can't be bothered to move them. It's only going to happen once at the start of the program. They're 32 bytes each. It's not a problem. Then within each of the sub-programs, where I'd had copy or create clauses, I replace them by present. Because I know the call tree, I won't use present or copy or present or create. I'll just use present. And that's when the performance jumps up. So now we're going faster than the CPU, and we're going much faster than all the kernels on the GPU, but no data region. Yes, there's a difference between here, but then this is one over the runtime. So as the runtime gets shorter and shorter, the jitter translates into bigger differences in the megops. This isn't a significant difference. And if I look at the Cray-ACC debug, I can go through and I can see that the only things that are being moved are these arrays, which are only moved once at the start of the program. So I'm not going to bother trying to minimize that data transfer. check the loopmark file. Were any kernels obviously badly scheduled? We've seen the examples of those. There aren't any more. Looking at the profile will alert you that there might be a problem, but just scanning through these loopmark files just to see if there's two little g's is always time well spent. So we now have the fully ported application, and we're getting good performance. You know, it's much faster than a single CPU core. Can we do anything else? What should we do? Well, we can do the same things that we did before. You can look at varying the number of threads per block for these 4 kernels. So here, the 4 kernels are the 4 different colors. Here, I'm at the 4 kernels with 64 threads per block, 128, 256, 512. If I look at the blue for resid, the minimum's at 128, which was the default. In fact, if I look at all of them, the minimum is at 128. So in this case, the default compiler choice was actually best. But it was worth checking. And again, the way I do this is I would change the vector length in all of the kernels at once, and I would use a Cray profile to pick off the time for each kernel in that single run. So one run generates those 4 bars, one run generates these 4 bars, compiling for different numbers of threads. Performance tuning, what could we do? Well, let's look at the resid kernel. We've got an outer loop, a middle loop, and then 2 inner loops with generating some temporary arrays here that are then reused. What could we do? Well, we could try collapse if the loops were perfectly nested. What we could do is we could say, well, actually, you know, this temporary array is only being used to increase performance. Does it actually increase performance? You know, are we just interfering with the cache? You could just get rid of this temporary thing and just manually inline these lines. So this is one big IJK stencil. So instead of having 2 inner loops, you'd have 1 inner loop, no temporary arrays now, and the loops would be perfectly nested. Then we could try the collapse clause. It means a bit of change in the source code. We could put a worker clause on the J loop. We could try caching. What do we cache? Do we cache in the I direction, or the I and J, or the I and J and K? Usually it's the I direction is best. We might try tiling the loop nest. We've already looked at changing the vector length. What's best to do? There's no right answer. You have to try it. The best algorithm choice I could find was a single loop nest. So I get rid of this temporary array and just do it as one big IJK stencil. Use a worker clause for J, and cache in the X direction only, the I direction, and use either 256 or 512 threads. This seemed to be best for the different problem sizes, but one of the things about, even when you choose a problem size with Multigrid, it's running multiple sub-problem sizes as part of the algorithm. So, you know, this tuning, when you tune it for a particular run of the code, even there is an averaging going on over problem sizes because of the Multigrid algorithm running the same kernel with different sized arrays. Well, you know, what can we do? You could fuse the loops together. This gives a bit of a speed up. You could use the worker clause. You could introduce the cache clause. So here I fuse the loop nests, and I get a bit of a speed up for a lot of problem sizes. I can put in a worker clause. That gives me a bit more speed up, and then I can add the cache clause, and I get a bit more. Depending on the problem size, the size of these arrays, I get speed ups of 1 to 2, maybe 3 or 4. You know, good. Not brilliant. If you know, data movements was a much bigger optimization, but it's worth exploring. And, you know, I wrote a CUDA version thinking, well, okay, I'll write a CUDA version of this kernel and I'll hook it in. I'll explain how you might do that. And again, there's an example in the tar file in version 7 or 8, where I actually call a CUDA kernel from inside OpenACC. Because, I'll write a CUDA kernel, it's bound to be faster than OpenACC, isn't it? No, it isn't. In many cases, but not all, the CUDA was faster than the default scheduling of the compiler. But if I did my little bit of tuning with directives, I can beat both of them by quite a large margin. So thinking I'll write inline CUDA, it'll be faster, is not really true. I'm not a great programmer in CUDA. No doubt I'm not doing it very optimally. I wasn't using shared memory, et cetera, et cetera. But the point here is that unless you really know what you're doing in CUDA, you're probably going to be beaten by the compiler. Because the compiler team, they spent a lot of time optimizing stuff. So you've got to be better than all of them. I'm not saying you're not, but don't think just because I write it in CUDA, I'm bound to beat the compiler. Because here, I couldn't. So when I did my own code, I did some code changes. I got a bit of a speed up here compared to just the data region. Here I did some optimizations in the resid. When I tried my CUDA kernel, I managed to make it go slower. But the main point here is that optimizing the data movements was far more important than any tweaking of the kernel scheduling that I did. Overall, I got a speed up of about 5.5 times. Code is quite memory bandwidth bound, so 5 is about what you'd expect compared to the complete CPU. But we were only using one CPU core there. So really what I should do is I should go in and I should run the OpenMP version of the code and try and get the best performance. Now, this isn't an MPI version of the code, so all I can do is run more threads on one node. Sometimes the best thing to do is not to run 8 threads of OpenMP. Sometimes the best thing to do is to run 2 MPI ranks, each with 4 threads. But this isn't an MPI code, so, in the interests of fairness, I'm going to say this code is a serial code. I'm prepared to do OpenMP directives like I've done OpenACC, but putting the MPI in and all the Halo exchange is a bigger job. So I can do better on the CPU, but if I just OpenMP it, the best I could get was to get this up to about 15,000 compared to 27,000 on the GPU. So the final speed up was about 1.8. So the GPU is definitely faster. So it's worth doing. We didn't put that many directives in, but really, socket for socket? Couldn't we get, shouldn't we be nearer to 5 times with memory bandwidth? The reason is multigrid, it's an algorithm problem. Multigrid is supposed to be a faster way to solve this problem by changing the resolution. But some of the resolution changes that we make, we go to a grid that's really small. It's just too small to run properly on a GPU. There's only 64 iterations. That's 2 warps in one thread block. It's just not a great way to run a GPU. And the GPU is just going quite slowly for those things because it's a really slow serial processor. Cray-Pat-Loof profiling told us we had these small grids. So what should we do? Well, it's an architecture thing, and maybe is multigrid the best algorithm on a GPU? Don't know. If multigrid is the good algorithm, do you really want to cycle down to size 4 cubed? Maybe you should have gone from 256 down to 64 cubed and not done the other parts of the multigrid. But that's where you, as an application developer, as a scientist, as an engineer or whatever, you go in with that knowledge. You have to change the algorithm by knowing what the science is you're trying to do, or the physics or the engineering or whatever. That's not the fault of the hardware. That's the fault that maybe an optimization that worked well on the CPU, the multigrid algorithm, was just being taken to too many extremes on the GPU. So that's very high level. I've not really shown you any code. I've shown you a few directives, but not all of them, because you've got all of those in the source code, and you can look at those. It's supposed to lead you through the process and how you can use tools to help you with the port. They can't do everything for you. They don't help you to do the data regions. One thing I've not shown you in this, and which the practical does show you, is another tool called Cray Reveal. So again, It's a Cray-specific tool. Of course, I'm advertising Cray. But again, it's a tool that does a job. Why was it developed? It was developed because of all the OpenACC work that Cray was doing to help customers like Oak Ridge get their codes ready to run on Titan. And then, with CSCS and the application readiness here. For simple codes, knowing whether your variables are shared or private is easy. You just look at it. For complicated codes, where you've got arrays passed down a complicated call chain, where these arrays might be in shared module files or global data in C programs, working out whether these arrays should be shared or private is very difficult, because you may have an outer loop that's here, and then way down the call chain you've got inner loops. How should these variables be scoped? It's not easy to do, and it's easy to get it wrong. And if you get it wrong, the code is wrong. It runs, you get an answer, the answer is wrong, and it's very difficult to track those problems down. So what Cray developed is a tool called Reveal. And the idea of Reveal is twofold. First of all, it's a graphical tool, and it takes all this loop mark information that you've got, and the Cray profile information that you've got, and all of this information about vectorization and so on, and it pulls it all together into one way of exploring the code. And so there's instructions on running Reveal in the PDF. Please have a go, especially because when we did the tutorial at supercomputing, they're trying to run it on a data center hundreds of miles away. Here, you can get the graphical tools up relatively quickly, so please try it. So that's one thing it can do. But the extra thing that it can do is you can go to a loop and you can say, scope this loop. And what it will do is it will go in and it will tell you whether these variables should be shared or private. If it's not, and it gets it right, it doesn't get it wrong, but there are cases where it says, I don't know. And then you have to help it and say, well, actually, no, it's definitely shared. But the point is, you don't have to go through with every array doing that. It does all the ones it can for you, all the way down the call chain, all the shared data, and works out this should be private, this should be shared. And then it leaves you to concentrate on the few that it couldn't do. And it produces for you an OpenMP directive. If you're doing OpenMP programming, you're finished. That's what you need. It'll even check, if you've got an OpenMP directive, you can say, could you check it for me? And it will say, I disagree when you say this is private, I think it should be shared, or this should be a reduction variable, but you've not said that. If you're doing OpenACC, there is another step beyond that. The scoping, a shared variable, you've also got to think about the data movement. And at the moment, Reveal doesn't do that for you. But it does get you to the point of saying it's a shared variable, and then you need to put an OpenMP directive. You then can write an OpenACC directive that matches that. But where it said shared, you'll say, well, actually, that's copy in, that's create. There isn't a tool that will do that for you automatically. It's a very difficult task. But Reveal does get you that first step of telling you it is a shared variable, and you can then say and clarify for OpenACC what it means. Hopefully, in the future, a future version of Reveal might do your OpenACC for you. They're working on this, but it's turning out to be for simple cases it's easy, but for complicated cases where you've got a lot of runtime dependencies in how the code is run, it's very difficult to sort that out. It'll probably need some sort of runtime feedback in order to do that. This is coming, they're working on this, it's not here yet. But the Reveal tool is great. I know I'm advertising it, but from your point of view, you may say, yeah, but I don't want to be locked into Cray tools. I run in other places. It produces OpenMP directives. OpenMP directives, Cray cannot put any sort of DRM, digital rights management, on this directive that it will only work on a Cray system. That OpenMP directive is completely portable. And if you turn it into an OpenACC directive, it's completely portable. You can take it to any other system, and it will work. We accept that you might do this, but we know that you will also be running on Cray systems, and we want you to be able to use those to the best advantage. So please use these tools. That's the big message. People are very nervous. They don't want vendor lock-in. What happens if we don't support Reveal anymore? It doesn't matter. It's done its work for you. It's produced these directives. So please use it. Please tell us if it works. Even better, tell us when it doesn't work, or if there's something else you'd like it to do. I mean, people always said, can it check my directives that are already there? So this was put in because people said this is really useful. So, you know, I might sound like a salesman, but I don't get any commission, and it doesn't cost you any money to use it. So please do that. So I haven't talked about porting a parallel code. I think while it is fresh in your mind, it might be better if you have a go at that practical. Does that suit people? What time has anybody got any hard deadlines to leave? I'm not saying we'll go on very long, but if I did a short talk at 5:30, is that okay? Anyone got trains or planes or anything? Right, okay. So why don't we have half an hour then of you having a go at that? So look at the PDF that's there, use that as the guide, and then you can either compile the different versions of the code to explore the tools. So the first part of the document leads you through compiling the code, running the code on the CPU, using the reveal tool, getting some loop level statistics on how it runs. And then after that, it actually does the OpenACC port. If you really don't want to do the tool stuff now, and you just want to get straight onto OpenACC, well, then you skip on to whatever it is, section 3, and you just go from there. So that's up to you if you want to do that. You don't have to do the reveal scoping in order to do it. There's different versions of the code that with each of the, incrementally adding extra directives in. So if you want, just run one version after the other. If you really want to go in and do it yourself, start at version 0 and start putting the directives in yourself. If you get a problem, you can always cheat and look at the other versions of the code to see what you should have done, or you put your hand up. So, it's up to you how you do it. Or if you want to talk to me about something else entirely, and use the time. It's hard to know because this example has kind of evolved over time with different things. Trying the different loop schedules, actually putting the code in, putting the directives in and compiling the code takes almost no time. This benchmark runs really quickly, it compiles really quickly. What can take the time is if you've got, 3 or 4 different ways of scheduling the loops. Each of those you may or may not be using a cache clause. You may be investigating caching in 1 dimension, 2 dimensions, 3 dimensions. You may also want to change the vector length. Running all of these versions takes time. Grepping the values out of all the results files takes time. Working out which is best takes time. But this isn't OpenACC. This is kind of just this tuning process. You spend more time kind of pulling the data together. An auto-tuning framework would make things easier for that. And if you're going to do this in production, that's probably what you want to investigate. If you're just kind of investigating stuff, then you can spend a little bit of time doing this. I mean, the thing about OpenACC is that, as I say, you put one directive in, you take the directive out, you recompile. If you want to change the loop schedule in CUDA, it's a lot more work. All this thread IDX, block IDX. If you want to cache in shared memory, you've got to do it twice, because you have to have a separate thing to pack to first pack it, then async threads, then you do it again for the actual kernel. Doing it in OpenACC is a great way to get stuff going and investigate different things. And quite often it will, OpenACC is different to CUDA, but it can give you some ideas of what's useful. If you want to investigate CUDA, I'm not saying CUDA won't beat OpenACC, because it can. Because, you can always use low-level stuff that the compiler won't necessarily know to use in this circumstance. But leave that until the end. get an OpenACC port that's working, because there were all these tiny little routines. I don't want to write a CUDA kernel for them. I'll leave them as OpenACC forever. I'll just write tuned CUDA for the very important computational routines. In the same way that if you're the type of person that uses assembler intrinsics, you don't use them in everywhere, you only use them in the routines that count. So it's OpenACC, the data regions are brilliant for just managing data movements in a way that, writing CUDA mallocs, CUDA mem copies and everything is just a bit tedious. It removes some of this work. It makes it a bit easier, there's fewer mistakes. And you can always keep that framework and call CUDA from within there. I haven't explained how you do it, but it's easy. If you want to see, you can already see by looking in whatever version 7 or whatever of the code in the resid routine. So, it's how long is a piece of string? The tuning, how long do you want to take? I can't say I've investigated every option. There's always something else you can try. You're always kind of walking along and you suddenly think, I better try that. And then, you have to write it down so you don't forget. It's how much time you want to take. And, kind of the tuning rule, especially if you've got a parallel code, is that quite quickly, you have a code that's compute bound, you OpenACC it and get the data movement sorted out. And now, GPU compute is really quick, and your code is now network bound or IO bound. Optimizing the kernels, whilst it might be fun, isn't the best thing to do. At that stage, you want to sort out your MPI or your IO, and then, if that improves, and then suddenly the kernels are the slowest thing again, go back to them. But, work on what's slowest, and sometimes the GPU is just fast enough. So I admit this document is quite daunting. There is a lot of pages. I keep trying to make it shorter, and then I keep thinking, but I must have mentioned this. But there are very few references. There's very few books you can go and read about actually porting an application in OpenACC. So this is kind of filling a little gap there in its way. I think John Levesque is writing a book, but I don't know when that's going to come out. John Levesque and Jeff Larkin, who now works for NVIDIA, but was part of the Oak Ridge team. Should be in Practical 3. So Practical 0 was just the silly little test. Practical 1 is doubling the array. We've not really looked at that, but this kind of just shows you what you would do for Fortran and C with dynamic arrays or whatever. So Practical 2 is the Himeno, and then Practical 3 is the Multigrid. So the build system, the make file, is all basically what you get with the Nass parallel benchmarks. And then there is a submit script that you use in the same way that you did for the Himeno. Well, what you would have to do then is you would have to move the data back to the CPU. It's not much data. It might work. There's no real overlap because everything in Multigrid, every kernel depends on the one before. So there's no way to kind of start moving the course data and do a medium resolution grid on the GPU while the data's moving. It all has to wait. It's possible. I haven't tried it. Yeah, it's not a lot. It might be that there's not a lot of data. It might actually be worth it. I've not tried it. Have a go. But what you would have to do is you would have to have two versions of, say, the resid kernel, one compiled for OpenACC and one compiled for not, or you'd have to start playing with the if clauses, which it's up to you. That's one way to do it. The other way is to say, what is the idea of multigrid? It's a faster way to solve the fine grid problem. But, it's supposed to be faster. If it's not faster, maybe you shouldn't be using multigrid, or maybe you shouldn't be going through all of those grid resolutions. But the answer might change slightly in doing that. It might still be correct, but it might change slightly because of the order in which you've done the iterations. So it's you as a scientist that has to say, but the answer is still acceptable. A climatologist wants to run their code and get exactly the same answer. Even on different architectures, it's very hard. But for CPUs you can do it, but it means changing a lot of the optimization levels to do it. But they prize that more than extra optimization. But you might say, well, look, I'm solving this problem as long as the residual is small enough that I feel I've solved the problem. Whether I use multigrid with all the levels or multigrid with some of the levels, or I just do a straight Poisson stencil on the original grid, I don't care as long as the result reaches this convergence. But I can't tell you what's right or wrong there. The point is, by using the tools, you start looking and saying, well, how many loop iterations? And it starts to point you at why the performance might not be as big as you expected. Well, within the multigrid, I think even in the input file, if you know what you're doing, you can tell it how many levels of grid resolution to use. Well, if you want to do some on the GPU, some on the CPU, it starts to become a little bit more complicated to code it up. And then you have to say, is it worth the complication? How much performance will I gain? It might be slightly faster on the CPU, but there is data transfer. Does it make it worthwhile? I don't know. If it gained you 10%, is 10%, is 10% important to you or not? Some people will say, yes, of course. Other people will say, I don't care, because it's going to take me 2 hours to process the data, to post-process the data file. So I don't care if the GPU is 10% faster or slower. A factor of 2 quicker than the CPU was good, but the rest I'm not so bothered about. It's hard to say. It's up to you. It's like optimizing on the CPU. How much effort you make is. Some people make no effort. That's why the Cray compiler, by default, is at level 02 of optimization. Because there are a lot of users who simply compile and they never look at optimization. So these people at least get some optimization on their codes. If the AVX generation is used by default, whether or not it depends on whether your CPU supports it. So, but that's controlled by the Cray PE Interlagos, Cray PE Magnicor, or whatever. Cray PE Sandy Bridge, Cray PE Ivy Bridge will decide, what level of that. Yes, yeah. I think with the Cray compiler you get some AVX by default if the architecture supports it. But I think with Intel you have to switch it on. It depends. It's worth checking the compiler price. But some people never optimize at all, and so they get O2 and they didn't even realize it. Is the example working? Everyone's very quiet, very studious, but has anybody got any versions to run? No. One person, right. At least it works then. Again, there's the make file, there's a submit script. If you really like doing things by hand, the make file shows you the compiler commands it was using. You can type those by hand if that is what you want to do. It's down in here. I didn't. They're not. Yeah, sorry. Those aren't all of the output files. These are all of the lines are of course important, but I've just highlighted the ones that are most important. Yes. When I first started with Cray and I started working on accelerator directives, I used double complexes and immediately broke the PGI compiler with its accelerator directives. But to my amazement, it didn't break the Cray compiler. And I mean, you know, complex exponentials and so on was not something that PGI had really spent any time on because no one used them. But I just used them, you know, by default, so because I had an old code to do that. So it should work. There should be no problem with us with supporting that.
Also not a performance problem because you frequently use, you know, memory access that are not sequential and square roots and stuff like that.
There's going to be I mean, there's a performance hit in general. I mean, any complex operation takes more flops in general. And you could potentially have strided memory access, and then it comes down to, it should still be faster. Whether, you know, you could optimize this by packing all the reals in an array and then packing all the imaginary parts. But that would mean restructuring your code and explicitly doing all the complex maths. And you would probably want to run a few test cases to see what the performance difference was and whether it justified tearing your entire application to pieces. You know, I mean, if complex maths is what you need, you will pay a performance penalty for doing that. And as long as that is not too great, it should still justify using a GPU compared to a CPU. Yes, so clearly the best thing you should do is never use double precision and never use complex numbers. But the real world doesn't always work that way.
Are you here tomorrow morning?
Yeah.
Are you going to other lines for tomorrow? It's just...
I might do a little bit of talking tomorrow morning,
Perfect.
but otherwise leave some time for practicals and discussions.
Yeah. Well, we'll continue.
Yes. I mean, porting a real code to OpenACC is hard work. There's no denying it. It's OpenACC makes it a bit easier than a lower level programming model. It's a good way to get stuff going, even if you want to use a higher programming model. But there is work to do. I mean, but you know, the payoffs are there. That even with this, where we say, you know, it's not optimal, it does have these really small grids, maybe we should change the algorithm. But even if we don't, and we say, you know, 64 loop iterations is stupidly small, we're still going faster than running on the CPU. You know, we're going 1.8 times faster than a single socket CPU. So what if you compared to a dual socket, which didn't have a GPU and had an extra CPU instead? Even if you had perfect scaling across them, then that would be 0.9 times faster, and the GPU wouldn't be quicker. But you won't get perfect OpenMP scaling across an entire node. Well, I'll be very impressed if you do. So I think even there, the GPU will still beat the CPU. You know, some people will say, well, you know, it doesn't beat it by enough to actually justify doing this port. But multigrid is, as I say, the algorithm is not optimal for running on the GPU. And the algorithm is only there, really, because it's supposed to be, you know, using multigrid is supposed to increase the convergence rate of your iterations. But if it doesn't increase it, it's not a it's only a performance enhancing algorithm. It's not supposed to, you know, there's nothing fundamental about it. So we should really change the algorithm. Oh, this is because, yeah, I'm sorry about this. This document is, I updated it for XC30. So you shouldn't load the Sandy Bridge, you would load the Interlagos module, Cray Interlagos. The setup script will load the right one. But all of the results that are shown in this document are for Sandy Bridge XC30 machines. So this is what Daint will look like when you get access to it. But Turdy is the older architecture. So the results that you're going to see are going to be slower on Turdy than you will see printed in this document. But hopefully, when you go and run on Pete's Daint, you will see that the numbers are basically equivalent. These numbers will run, I forgot to mention this. If anybody is interested, we do have some temporary training accounts on a Cray machine called Swan, which is the same architecture as Daint. So if you were interested in running on that, it's got GPUs, same GPU, same CPU. If you were interested in running the examples on that, we can give you a temporary account on that if you want to do some comparisons. I mean, the good thing about the Cray XK7 and the Cray XC30 is that the programming environment is very, very similar. The tools are the same. The way you use the compilers is the same. Most of the changes are all going on underneath. The change in the network, the change in how the MPI and things work, the change in the compiler optimizations for different CPUs. You have different modules loaded that put these different compiler commands in. But it's almost compile and go to move to the new one. Yes, you can tune for the new architecture, CPU or GPU. But these examples will run on either one. So if you do want to use this other machine, we can give you a training account relatively easily, except we need to print out the passwords. But so yes, all of the numbers that you see in those documents, the performances will all look a bit higher than what you're seeing on the XK7. But the overall conclusion is the same, that the GPU is faster than the CPU, but not quite as much as we expected because of this scheduling thing. Is anybody using the C version? I'd never asked this at the beginning. I mean, what languages do you usually use? I mean, who would usually use C? And who would usually use Fortran? And who would usually use C++? So it's quite an even mix. C++ is getting, we see more and more people using C++. We weren't allowed to say it at the time, but OpenACC 1 was not very good for C++. OpenACC 2, probably most of OpenACC 2 is trying to make C++ easier. It's not there yet, but it's easier. There's still improvements to be made, but what we really need is people doing C++ with OpenACC and just saying, how do I do this, how do I do that? This is broken. I mean, if you're prepared to sort of work with us on this, where things don't work or where things that you'd like to do you really can't do, both from a sort of compiler point of view and also a standard evolution point of view, user input is very important. So in the C version, it's kind of slightly embarrassing in that the C version of the code, the first thing it does is rewrite the code. So if you look at the version 00 orig, it's got the way the arrays are allocated is the way you would typically allocate arrays in C, multidimensional arrays, with nested malloc statements. But in OpenACC 1, that was just not supported at all, to which people would just say, but that's the way C works. How can you say you support C if you don't do that? So in OpenACC 2, the support for these sort of recursively malloc arrays has been improved a lot. The danger is that you don't know that when you do these recursive mallocs, that you end up with a contiguous block of memory for all the pieces of the array. Of course you always do, because that's what all the compilers do. And so what's happened in OpenACC 2 is that you can, since the compiler allocated the memory, it should know whether it's contiguous or not and should be able to deal with it. And so you can use ragged arrays. You can, as long as they're rectangular, you can have recursively malloc things. So if you look in Practical 1, there's an example of using that. Slightly embarrassingly, it didn't work for Practical 3. So when I filed a bug, they said, yes, it's been fixed. It'll be out in the next release of the 8.2 compiler. So I said, when's that coming out? And they said the 5th of December. So it'll work tomorrow. So flattening those arrays using a single array index, you should be able to avoid doing that and just take the original code. But there is a workaround in the version that you have because there was a compiler issue that will only be released tomorrow. So I will endeavor to update that version of the practical. So if you want an up-to-date version, you should contact me and I will give you one when I have it. Yes, yes. So I'll give you I'll just give you a card, and that's probably the easier way to do it. So it's got my email address there, yes. So if you've got any questions about it. So how long do the course accounts last for? Presumably it's for 3 days, is it? Right. So, yeah, so you've got time to copy this stuff off.
Oh yeah, I did
Yeah.
copy it.
Right. But your computer's dead, right, that's fine.
Yeah, because I have British.
Yeah. It's really a set of, it leads you through the entire process of porting that code from the point of view that we will treat this like a real code. So how do we know where to start? How do we work out how to scope the variables? How do we do all these things? What tools are there to help? So to do the whole thing and work through all of that, this is quite a job, and it takes a lot of time, and it's more time than you can really give in a day's course. So This is why the document kind of is fairly wordy. It has results in it. It has screenshots. It's designed to be something that you can sit down and read afterwards. You can sit down and read it on its own. It's better if you can look at the source code as you go. It's better if you can even run the source code whilst reading the document and check the results and see what happens and check all these things. So you get some time to do this today. There's some time tomorrow in the morning when you could do that. You know, you can do a bit more while I'm talking or whatever, however you want to structure it. But it's kind of a take-home document as well as being a guide to this practical. And yes, it could be made shorter, but I don't think it would convey the same sort of information. Because porting a big code is a big job, and you know, a real code is even bigger than that. But this is supposed to give you some more things that you can do when you're dealing with that code. So you may have seen the Nass parallel benchmarks. You can download them from the NASA website. There's a set of codes in there. Although they're called the Nass parallel benchmarks, I'm actually looking at the serial version of the code. There's a serial version in there. So it's running on one node. I'm going to be parallelizing it to run on one GPU. So it's not an MPI version of the code. We do have an MPI version that's been OpenACC'd as well. I think that's in the parallel code directory of the tar file, just as an example that can be used perhaps in the next days. So, sorry, I said it was 600 lines. It's about, you know, 1,000 odd lines of code. So it's a bit bigger, it's a bit more complicated. The PDF has all the instructions for building the code and running the code. When you run the code, much like the Himeno, you get some part of the output file. There's a checksum. It also verifies whether the checksum is correct, and it times the execution and converts that into a performance figure. And again, we use that performance figure as a metric. There's a Fortran version, there's a C version. You can choose which version you like. So what do you do? Where did we start? The first thing you should do is you should profile your code running on the CPU, because you want to understand something about how the code works. So the first thing you do is you just profile it using, so you do a pat build, you do a tracing experiment using the -u flag to say, trace all my user functions. And when you do that and you get the .xf file and you look at it, you get a profile that looks something like this. The performance figures in this talk are for XC30. So if you run on Turdy, the numbers will look slightly. So to continue, we talked about handling asynchronicity just now, and it's kind of a tricky thing to deal with, you know, sort of to understand, especially these sort of asynchronous waits. And usually the best thing to do is to do it by example. And the example that I was going to talk about was porting a parallel code, but I'm kind of conscious that time is going on, and it would be good if you had some time to try the last practical before the end of today. I'm around tomorrow morning, so I can talk a bit more about asynchronicity then, or we might be able to fit it in at the end of today, but it would be a shame if you hadn't had a go at trying a bigger code practical. Now, practical, the last practical, which I think is practical 3 in that tar file, is the Nass parallel benchmark multigrid code. It's a bigger code than the Himeno code. I mean, it's a big 600 lines, which still isn't big in the sense of, you know, a real application. But the structure of the code is much more realistic. It's got a more complicated call tree. Its data moves up and down the call tree. When you first open the file and look at the code, you can't sort of see the structure immediately. So the practical, along with the practical, in that directory, there's a PDF file. And that PDF is an enormous document. It's about 19 pages, which, you know, is quite frightening. But the idea of this is that it's not simply a list of things to type, to enclose calls to the routine. So we're getting this information without even looking at the source code yet. by doing a profiling and getting this call tree view. The next thing you want to know is, okay, it's all very well knowing which routines take the time, but are they suitable for GPU? Do they have loop, is the runtime of the routine, is it due to loop nests or is it due to serial code? If it's due to loop nests, how much work is in those loop nests? If they have really small trip counts, it's not going to work very well on a GPU. Again, simple application, you just know what the trip counts are. For a more complicated application, it's not so obvious. This is a multigrid application, which means that it processes an array, but it processes it by sort of coarsening and refinement processes, whereby sometimes it's averaged the array down to be very small, and then it interpolates it back to be big and does processing at all these different resolution levels. So the number of trip counts depends on how it's calling the routine. And if you've got a real application, it's not obvious how many trip counts there are in a loop. So this is very useful information. So the Cray compiler has a way of, you can compile the code with a special flag, and then when you do a CrayPat profile, the profile isn't done at a routine level, it's done at a loop nest level. And that's really useful. So the information we can get, here I'm only showing the information to do with the most expensive routine different, because the CPU is different. And also the architecture of the blade is different. So even some of the GPU figures can look different, because the integration of the GPU into the CPU via the sort of bridge chipsets is different. And XC30 tends to perform a little bit better even for sort of pure GPU. So when you run it, you see that there are essentially 4 routines that dominate the runtime, with this proportion of the runtime. There's other routines that are executing, but they take less than 1% of the total time. When you do a PAT report, by default, anything taking less than 1% of the time isn't shown. There's a flag minus capital T if you want to see everything. The point of these is that insignificant routines can still be needed in an OpenACC port because you want to process data on the GPU all the time. So you can also do a PAT report and ask for a call tree view. So this is the same .xf file, you just report it in a different way. Again, the PDF has the exact instruction to use. When you get the call tree view, it's showing you these 4 routines again, but now it gives you some idea. There's a main program, which is called MG. MG, if you look at the indentation levels, calls 2 different routines. It calls MG3P and it calls resid. MG3P then calls these 4 routines. So you can see that resid is called from 2 different places in the call chain. Understanding the call chain of your application is very useful because when you put the data regions in, you want to know where to put them